Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about the conservation of angular momentum. We said when the net external torque acting on a rotating object is zero, then the angular momentum remains the same. In other words, the angular momentum is conserved. Today we'll talk about a different concept, and that is rotational kinetic energy. What is rotational kinetic energy? Last year, or you can say previously, we've learned about kinetic energy here. What is kinetic energy? That is, if we have an object, if this object is moving, clearly it has a certain mass, and if it is moving with a certain velocity, then this object has kinetic energy. What is kinetic energy? We can say the energy due to movement, or any object that is moving, especially if it is in a straight line, this object would have a translational kinetic energy, and the equation of this one was 1/2 mass times velocity squared. Kinetic energy was a scalar quantity. It was measured in joules as well. All kind of energy, it is measured in joule. Doesn't matter whether if it is kinetic energy, potential energy, electrical energy, sound energy, or whatever the kind of energy is, they're always measured in joules in here. But remember, that is for translational motion. That is for an object that is moving in a straight line. What about this here we have? Because we're dealing with objects that are rotating, so we can say if an object is rotating, instead of having kinetic energy, it has another type of energy, which we call it rotational kinetic energy. For example, if you have an object, a disk or whatever the object is, if it is rotating, it has a type of energy due to its rotational motion that is called rotational kinetic energy. So what is rotational kinetic energy? Rotational kinetic energy. All right, let's just write it nicer. Rotational what? Rotational kinetic energy. So what is the equation for that? It is the same equation as we have in translational, but of course for angular quantities here. So we can say kinetic energy, we'll write R for rotational energy. All right, for rotational kinetic energy, it is equal to 1/2. And then if you look at this equation, we have mass in translation. So what is the analog of mass in rotation? That is moment of inertia, that is first. And then instead of velocity here, we have angular speed squared. That is clearly kinetic energy of what? Of rotation, or you can say in rotational kinetic energy in rotational motion. Once again, we said all types of energy are measured in joule, so this is measured in joule, and that's it. And you can say, or you can tell what joule is equal to. If I the base units for this one, that is going to be the unit for moment of inertia. You do know that that is kilogram meter squared, and then for angular speed, meter squared, for angular speed it is radian per second. But clearly we've learned before that whenever we combine radian with other units, because radian is dimensionless, we're not going to write it, or we'll just ignore it. So it's going to be kilogram meter squared over second. So these two are, you can say, or this, it is equivalent to joule, which is a unit of energy, work done, or any other types of energy here. So that is rotational kinetic energy in rotational motion. That would be the energy of any object that is rolling or rotating. Okay, so now we've learned so we can emphasize the difference between the two here. So this would be the kinetic energy in translational motion, and this would be, it is analog, which is kinetic energy in rotational motion. Once again, 1/2 mv squared, that is for translation. It is equal to, or it is equivalent, so it is analog in rotation. That would be 1/2 moment of inertia times angular speed squared. Okay, now, but if you remember, we've learned about if the angular momentum is conserved, we said angular momentum, it is equal to, or if angular momentum is constant, it is equal to moment of inertia times angular speed. Is that true? Let me just write it at a side perhaps. All right, angular momentum, it is equal to moment of inertia times omega, or angular speed. So if I want to substitute this into kinetic energy of rotation, watch this, 1/2 moment of inertia times angular speed, yes? What happens if I substitute these values into this equation? See what I'll get. So for example, if I want to make the moment of inertia the subject here, it is equal to what? It is equal to L, moment of, or angular momentum, divided by angular speed, as you can see. So if I rewrite this one, substitute, see what I'll get. This is the main equation, don't forget. Now we can get another equation, kinetic energy of rotation, it is equal to 1 over 2. Instead of moment of inertia, I'll just write L over omega, and then that is multiplied by omega squared. 1 omega cancels with 1. So what is the equation that you're left? We can say kinetic energy of rotation, it is equal to 1 over 2 angular momentum multiplied by angular speed. So this is also another equation that you can use if you have angular momentum and then angular speed together. If you ever want to find kinetic energy of rotation, that is what we have. Okay, now what if I substitute, let's say, what if I make the angular speed the subject? If I want to make angular speed the subject, then that would be L angular momentum divided by moment of inertia. So what happened if I substitute this one here? So once again, kinetic energy of rotation, it is equal to 1 over 2 moment of inertia. This time, instead of angular speed, I'll write angular momentum over what? Over moment of inertia. But don't forget, this is squared, right? Oh wow, I forgot to mention this here. So this is squared. So if that is squared, this too, of course, also becomes squared. Now we can say 1 cancels out with 1. So what is left now? We can say kinetic energy of rotation, it is equal to 1 over 2 times angular speed angular momentum squared divided by moment of inertia here. That is also another equation that you can use just in case, for example, if we're given angular momentum and moment of inertia, that would be the kinetic energy of rotation for the object here. Okay, but don't forget that is for a constant angular momentum here, you could say. All right. Even if it is, you could just substitute if it is given here at this point. So now, what have we learned so far? Perhaps we did not even define kinetic energy of rotation. So we can say kinetic energy of rotation, yes, it is the energy of an object due to its rotational motion. In simpler words, we can say if there is any object that is rotating, their kinetic energy can be found using these equations here. This is your main equation here. And then, of course, we can use these two equations in case, for example, if you have angular momentum, and then angular speed or moment of inertia, and angular momentum too. All right, so this will be for that. Now, let's head on for a few study tips, perhaps. That is the energy of, don't forget the definition, it is the energy of an object due to its rotational motion. That is what is it equal to. It is measured in joules. That is the equation. Again, for translational, we have 1 over 2 mass times velocity squared here. For rotation, that is what we have. These two are analog of one another. And these are by substitution. We can get these equations here. Now, a few study tips before we solve or we go to questions or perhaps talk about the law of conservation of rotational, let's say, before we talk about the law of conservation of mechanical energy, as a matter of fact. So what do we have? It says the rotational kinetic energy, it is analogous to the translational kinetic energy. We've mentioned that, I believe, right? We said of kinetic energy of a particle, where the moment of inertia I replaces mass, all right? Give me a second here. And then after that, it says the angular speed omega replaces the translational speed, replaces mass, we said, and angular speed replaces, of course, the translational speed here. The second point says what? The SI unit of rotational kinetic energy is joule, and that is obvious to all kind of energy. Of course, whatever the type of energy it is measured in joules, so there's nothing surprising here at this point. Now, point number 3 says the conservation of angular momentum does not lead to the conservation of rotational kinetic energy. And that is a point where you have to be really careful at this point and make sure you underline this point as well. What do I mean by this? Do you remember the ice skater? Previously, we've mentioned that if the ice skater extends their arms and of course their feet, the mass would go, or the mass will be distributed far from the axis of rotation. So moment of inertia increases, angular speed decreases. That is, when the net external torque on the ice skater were 0. In other words, if the angular momentum is conserved, all right, remember this, that does not necessarily means the kinetic energy of rotation must also stay the same. Okay, that is what this point means here. Why? Because by extending the arm or bringing the arm in, the rotational speed of the ice skater were changing, all right? So, and that is a proof that the kinetic energy of rotation for the ice skater is not the same, even though the angular momentum was the same. So don't forget this. And we also said that previously in section 1, we said a point mass, if you remember, sometimes instead of telling an object, how do we know that object has rotational kinetic energy or not? You can always refer to if it is ever mentioned, whether if it is a point mass or extended object. If you remember, we said if an object is called a point mass, or if it is a point mass, then it has only translational speed, so no rotation, right? But if it is an extended object, then of course it has rotational, or it is rotating, so it has a rotational kinetic energy. So don't forget this. That'll be for point number 4. Okay. An extended object, that'll be for that. All right, now take a look at this question. This is also something important and once been in WZADI. By the way, lately, questions like this, all right, that even though it does not require math, but they can use this, for example, or to convert this written part into equations and formulas, and you're required to know the answer. That is one thing. And then another thing also, sometimes they can bring this as a multiple choice question. So once you see a question like this that is written or in words, don't underestimate that, because they can change this into, like I said, into equations where you have to do calculations, or perhaps into a multiple choice. So you have to be really careful about these kind of questions here. So what do we have? It says, an ice skater uses the conservation of angular momentum to produce high-speed spins when they bring their arms close to the axis of or rotational axis. In other words, when ice skaters bring their arms in, now they're going to rotate faster or spin faster, even though the angular momentum is conserved. What does the angular momentum is conserved means here? That means the net external torque is 0. Use the conservation of angular momentum. That means the net torque is, or external torque is 0, don't forget. Okay, so the question says, imagine that a skater moves her arms inward, that is a keyword, cutting the moment of inertia in half. What does it mean, cutting the moment of inertia in half? That means it is, or moment of inertia, it is going to become what? It is going to become half of the previous one, you could say. All right, that is, you can say moment of inertia final, if you want to call it. It is equal to half of the initial here. Half of the initial, or the previous one here. Okay, now that is the first part here. Then therefore, doubling their angular speed. Doubling their angular speed, that means whatever omega is, it is going to be twice as much now. So we can say omega final, if you want to call it, it is going to be 2 times the initial. All right, next says, if we consider the rotational kinetic energy, so we see that the energy is doubled. The rotational kinetic energy is doubled in this situation. Thus, the angular momentum is conserved, but kinetic energy is not conserved. Where does this extra energy or rotational kinetic energy comes from? First of all, before answering this question, I would like to explain this question a little bit here. So this is what we have. It says by let's erase this one here. So here's an ice skater. By bringing their arms and legs in here, it says the moment of inertia becomes half of the previous one here, cutting it into half. That is what happens here. We can say moment of inertia final is going to be half of the previous one. What about angular speed? Angular speed, it is going to be twice of as much in here. So we can say 2 times the initial one here at this point. You can even erase this one here if you want to. For example, you could just write this one at this point here, if you want to call it, or whatever it is. And then the question says, what happens, for example, that was, or this was in Wazari 1. So if that is the case, what will happen to the rotational kinetic energy? All right. So if I ask you, by cutting the moment of inertia into half, an angular speed, let's say double that, what would be the rotational kinetic energy? You might just, immediately say it might be whatever, 4 times perhaps, okay? But do not, throw random numbers without putting these numbers into equations. So let me tell you what I mean by this. So we know that rotational kinetic energy here, it is equal to 1/2 moment of inertia times what? Times angular speed? Yes, well done. But this is squared one, yeah? All right, so at this point, that is 1/2. The question tells you cutting the moment of inertia into what? Into half. So I can even write what I just wrote before in here. So cutting into this one into half, I can just say 1/2 times the moment of inertia, or you can say initial. Let's just ignore initial at this point here. Well, let's just write it here. And then multiply by 2 times, because the angular speed now, it is going to be twice as much at this point here. But don't forget, this is squared. And if you're not careful, you can say, because this is 2 times much, watch this. If you just plug this number into the equation here, and this is what happens when you're not careful, kinetic energy of rotation, 1/2 moment of inertia times angular speed squared. But if you're not sure here at this point, if you're not careful, you might just say, ignoring the moment of inertia, you might out of the sudden just forget about this one. It says because the angular or omega final becomes twice as much, so you might just write this one here, and you might say 2 squared, that would be 4. You can bring the 4 forward. You can say the kinetic energy might increase 4 times as much. But that would be incorrect. Why? Because it is true that the angular speed increases twice, but what happens to the moment of inertia? It becomes half, so you'll have to be careful at this point. So we'll just say 1/2. Let me write this as a different color here. That is moment of inertia times, this 2 becomes 4 times, right? That is, we can say angular speed squared in here. So now this 4 and, sorry, this is 2, my bad. This 4 and 2 cancels out, of course. It becomes what? It becomes 2. So now I'll bring this 2 to the front. So 2, that would be 1/2. What is left in the equation now? Okay, 1/2 moment of inertia times angular speed squared. Now, perhaps you see the reason why I wrote this in a different color. And you might say, why don't we cancel this 2 with this 1/2 here? I don't want to do that because this part in here, it is equal to what? It is equal to rotational kinetic energy. I want to know how many times did the rotational kinetic energy increase or decrease, like by what factor did it change? So now based on this, if I cancel out this 2, then what is left here, that would be moment of inertia times angular speed. That would not be the equation of kinetic energy of rotation. So I'll keep this factor here, all right, so that I can say, now I can see how many times it got increased or changed by what factor. So by cutting the moment of inertia in half, and that makes the angular speed twice as much, so that changes the rotational kinetic energy by 2 times, not 4. This is the point where I need you to be careful with at this point right here. That is 4. By the way, the angular momentum is conserved. So the question is asking here, where does this extra rotational kinetic energy is coming from? Basha, if there's no person helping the ice skater to spin faster or slower, where does this extra energy comes from? Isn't that violating the law of conservation of energy? Because we know that energy cannot be created or destroyed. Yeah, if that is the case, where does this extra energy comes from? Well, the answer to that question is this. If your arms are extended, the ice skaters are going to bring them in, right? So, but can the ice skater bring their arms in close to their body without doing some work? No. So their muscle, you can say here, they're using some mechanical energy, some chemical energy in the muscles to contract the muscle so that they can bring the arms in. Isn't that work done here? Yeah, so they're using internal body or chemical energy that is inside the muscle to bring their body in. If I ask you, for example, to bring this pen from this point to this point, can you bring the pen to this point without doing any work? The answer is no. But once you're doing work, of course, you're using energy. Is that correct? Yes. So that energy that you're doing work to bring your arms in, that energy converts to rotational kinetic energy, and now the ice skater spins faster. So now at this point, since we know the reason, this does not violate the law of conservation of energy. Why? Because, of course, once you're bringing the arm in, you're doing some work. That work converts to kinetic energy of rotation here. So, of course, this benenuzari, I hope you understood how or why. So when they bring their arms close to the axis of rotation, they do work. That work turns into rotational kinetic energy. When they bring, so this is the explanation. We can say when they bring their hands down, moment of inertia becomes half, angular speed doubles. Since the angular momentum is conserved, so kinetic energy, of course, becomes 2 times as much. But once again, be very careful here. If you're going to use these numbers into the kinetic energy of rotation, just do not just substitute this, substitute the whole thing so that you can get 2 times as much. Now, a question here. What does, actually, we've solved this one already when we're talking about the law of conservation of angular momentum. Today, now we have a kind of like a new concept, which is still related to kinetic energy, but now we have the law of conservation of mechanical energy. So we have something here. What is mechanical energy? Now, up to this point, let's say, or previously, we were saying mechanical energy, grade 11. We were saying mechanical energy, it is the sum of kinetic energy and potential energy, true? But now, because objects are rotating, there is another type of energy. So we can say mechanical energy at this point, it is the sum, it is the total of translational kinetic energy, rotational kinetic energy, and potential energy as well. Let me write this as an equation here. So mechanical energy, once again, previously or in grade 11, we were just saying mechanical energy. MA stands for mechanical energy. We were just saying kinetic energy plus potential energy here. Or you could say gravitational potential energy to be more precise. Kinetic energy, we're just saying 1 over 2 mass times velocity squared. For potential energy, it was mgh, right? Okay, but now, because we're dealing with the rotational objects here, so mechanical energy now becomes more than just this two here. So we have kinetic energy of, now of course we're going to call this one translational, because that is for an object moving in a straight line here, plus we can say potential energy, I'll write rotation or gravitational potential energy, this G, that would be gravitational plus kinetic energy of rotation. But we always write this two together so that you can, perhaps it is easier to remember. So kinetic energy of rotation plus gravitational potential energy, and that is mgh. So let me write the equation of each one of these down here. 1 over 2 mass times velocity squared plus, for rotation, we said 1 over 2, instead of mass we have moment of inertia, instead of velocity we have angular speed squared plus gravitational potential energy, it is mgh. That is mechanical energy, the sum of all these types of energy here. And of course mechanical energy, because it is energy, so the total of all these energies are still going to be measured in joules too. All right, now we're going to talk about the law of conservation of mechanical energy. What is the law of conservation of mechanical energy? We can say, if, can we say energy, we know that energy is neither created nor destroyed one, yeah? So, but it can change or transform, let's say, from one form to another, we know that. So in other words, if there is no energy lost, considering there's no friction, no air resistance, no energy is lost, we can say mechanical energy initial must equal to mechanical energy final. Okay, so once again, the law of conservation, conservation of energy, or using that, of course, we can say mechanical energy initial would equal to mechanical energy final. What does this mean here? So all the types of energy that we've mentioned here, kinetic energy of translation, kinetic energy of rotation, plus potential energy here, gravitational, these are all initial must equal to what? Kinetic energy of translation plus kinetic energy of rotation plus potential energy, gravitational, that would be final. But you're not going to need this one much because we have some other things that I'll tell you what you need the most in here. What exactly we use this one for? For example, if an object is going to roll down here, any object, let's say. So at this point here, let's say at a certain height, right? If this object is at a certain height, then let's say this object is at rest, whatever the energy of the object at this point, if we assume no energy is lost, by the way, so we can say mechanical energy initial here, all right, it is equal to mechanical energy at the bottom of the incline. That is when, if we assume that there is no energy lost due to the friction, due to the air resistance, or could be any other factors that might affect the energy of the system here. So what exactly do we have now? Now, stay with me for a second. We have something very important and you need to be aware of this one now. So here, let's say we have an incline. All right, so there we have an object, let's say a sphere perhaps. This sphere is at rest. What is it? It is at rest, don't forget. All right, how can we apply the law of conservation of energy? Let's call it solar sphere, by the way. Solar sphere. How are we going to apply the law of conservation of mechanical energy to this sphere? Once it is at the top, and then after that, this sphere, it is going to roll down to the bottom of the incline here. That is the same sphere. Okay, so at this point here, we can say that mechanical energy at the highest point here, it must be, if we're applying the law of conservation of energy, it is equal to mechanical energy at the bottom. This is the law of conservation of energy. So what exactly are we trying to use this for? We have questions like this. An object that is rolling down, right, at, let's say, a certain height from or on an incline here, the question will be asking, what is the translational speed of this object at the bottom of the incline? So how can we tell the velocity of the object or translational velocity of the object at the bottom of the incline? Well, we can only do that because at this point here, whatever the energy of the object, it is going to convert into what? Into, let's say, kinetic energy there, and then using kinetic energy, we can find the translational velocity of the object right at the bottom of the incline. But there are a few things I need you to learn before we do this, right? First of all, at the highest point of the object is at rest. So let's say this is a certain height, okay? So whatever the height is, later we'll give some numbers too. So at this point here, if the object is at rest, what is the mechanical energy equal to? We know that mechanical energy here, it is equal to what? It is equal to kinetic energy of translation plus kinetic energy of rotation plus gravitational potential energy here. Okay, but here's a question. If the object is at rest, that means it is not moving, neither rolling, true? Or neither moving nor rolling here. So if the object is at rest, can I say the kinetic energy is 0? Yes. If the object is at rest, can I say the object is also not rotating, so the rotational kinetic energy is 0? Yes. But if the object is at rest, it is at a certain height, so it has gravitational potential energy, right? Because gravitational potential energy, we've mentioned earlier, gravitational potential energy, it is equal to mgh. So it doesn't matter whether if it is moving or not, as long as there's a certain height, there will be gravitational potential energy because that is the type of energy which is related to the position of the object or how high or low the object is. So can I say at the top of the incline the object has only gravitational potential energy, which is equal to mgh? That is what we have, and you can call it initial, by the way. Okay, but then once this object is rolling down, all that energy, it is going to convert to both types of translational and rotational. Let's see how. Now, mechanical final, once again, it is equal to kinetic energy of translation plus kinetic energy of rotation plus potential or gravitational potential energy here. Okay, obviously once it is at the bottom here, it is still both moving and rolling at the same time as well. But the question would be asking what is the translational speed. We know that for kinetic energy, It is equal to 1 over 2 mass times velocity squared, so it has a certain velocity. What about kinetic energy of rotation? That is 1 over 2 moment of inertia times angular speed squared. It is also rolling, so we have these values. But what about potential energy? We know that the height is at the bottom. What is the height at the bottom? Isn't the height 0 here? Yes, if the height is 0, what is potential energy? It is 0. So we can say potential energy at the top, all right, of the top of the incline or whatever, it is equal to the kinetic energies at the bottom of the incline here. So here's the question: how can I find the translational speed for the object? Well, you have to follow up with me at this point here, because we're going to do some calculations, but I'll only do it once. Why? Because later you don't need this. We'll just skip to the last step that we have, and then you can always use that step without any hesitation, inshallah, without making any mistakes. So stay with me while we're going to do this one here. So how can I find the translational speed if I have the potential energy here? How about we go to another page perhaps? Okay, so let's give it a try. So at this point here, we said the highest point we have only gravitational potential energy. That is, let's just call it mgh, right? And then at the bottom here, we have both types of kinetic energy of translation plus kinetic energy of rotation here. So can I say these two are equal? Because if we're saying that the law of conservation of energy, as long as it holds, these two must be equal to one another. We said at the highest point, we have, let me just rewrite it perhaps one more step, translation plus kinetic energy of rotation plus potential energy, gravitational. It is equal to, these are all initial, don't forget, it is equal to kinetic energy of translation plus kinetic energy of rotation plus potential energy, and these are all final, don't forget. We said these two parts are 0 and 0. If the object is at rest, don't forget, we only have potential. What is potential equal to? mgh. It is equal to kinetic energy. We have this and this value. We said this value is 0, potential energy at this point. At the bottom of the incline, potential is 0. So you could say final. So what is kinetic energy equal to? 1 over 2 mass times velocity squared plus, and then kinetic energy of rotation, 1 over 2 moment of inertia times angular speed squared. Right? Oops. All right. So here mgh. All right. So now at this point, what about the moment of inertia for this? We said this is a solid sphere. It could be any shape, doesn't matter. What is the moment of inertia for a solid sphere? That is 2 over 5 mass times moment of, all right, so mass times radius squared. Yes, right now. What about angular speed? We know that. Can I say it is equal to tangential over the radius? Yes, but watch this. It could be any shape. So for any other shape, can I just call this one C? Because C could be for any shape. Whether if it is a ring, a point mass, a solid sphere, or a thin spherical shell, a coin, a disc, it doesn't matter, right? I'll just call that C here. So one more time, mgh, it is equal to 1 over 2 mass times velocity. By the way, like I said, I'll just do this one once and I'll never do it again. So plus 1 over 2. Instead of moment of inertia, we said we'll just write C, that is a constant. All right, should have been 1 over 2. Let's make this one blue. Constant times mass times the radius squared, and then multiply by what? Multiply by tangential, because this is squared, so it's going to be squared over radius squared. And these two cancel out. So what is left now? Once again, mgh, it is equal to 1 over 2 mass times velocity squared plus, again, can I bring the C to the front? Yeah, so C times 1 over 2 times mass, because these two just got canceled here, tangential squared, yes? Now I want you to notice something here. Do you see these two terms are, I'll just write it better. These two terms are exactly the same, yes or no? Can I take a common factor? Yes, but first, let's just write mgh here again. It is equal to, I'll just take the whole thing as a common factor, 1 over 2 mass times velocity squared. So if I take this as a common factor, what is left in here? Just 1. Plus, what is left on the other side is just C here. Now, only for those who did not get this part, perhaps, let's say you have something like this, x plus 2x, let's say, right? So if I want to take x as a common factor here, how do you do that? What is left in here? Just 1, because there's nothing left. Plus, the other side is just going to be 2. That'll be x in here as a common factor. Here, there will be just 1 left. That'll be this one. And then here, it's just going to be this 2 here. I did exactly the same at this point here. Okay, so let's erase this one. I'll show you somebody, you know, like judge or whatever. So what is left now? Can you see the difference at this point here? Can I cancel out this mass and this together? Yes. I need to find this V here. And of course, this side were initial, this side is final. So don't forget, I can make this one final. Okay, so just remember this one here. So what is left on this side? GH. I'll cancel out mass because that'll be the same object. Plus or equal to 1 over 2. 1 plus, oh wow, 1 over 2 tangential squared 1 plus c here. Okay, so one more time, how can I get rid of this 1 over 2? Okay, multiply both sides by by 2, or just multiply this to cross multiply, right? So if not, you could just multiply both sides by 2. If I just multiply by 2 here, this to cancel out, yeah, like that. Right, so 2 times GH. Let me just keep what I wrote in here. 2 times GH, that is equal to, let's just call it 2GH. It is equal to tangential, or just velocity squared, 1 plus c. We're almost there. I want velocity, so how can I find or make the velocity the subject? Can we divide both sides by this factor here, or you could just bring this one under this. Okay, that is this. If not, just divide both sides by 1 plus c. So if that is the case, we can say tangential or velocity squared, it is equal to 2gh over 1 plus c. Yes or no? Very good. But I want velocity, not velocity squared. So we'll say velocity, it is equal to take the square root for both sides, it is equal to the square root of 2gh 1 plus c. And that is the equation that you will need at this point here. But what is c? Don't forget, but this c, it represents the shape that you're using. For example, for a ring, for a point mass, it is 1. For a disk, it is 1 over 2. For a solid sphere, it's 2 over 5. For a thin spherical shell, 2 over 3. And then whatever the shape that is rolling, that'll be this C4. So hereafter in calculations, the only thing that you need to know is this V here. That'll be translational speed. And of course, this is final 2 here. It is equal to the square root of 2gh1 plus c. That is for any object that is rolling down on an incline. If they ever ask for the tangential speed at the bottom of the incline, that's first here. By the way, if the object goes from the bottom of the incline to the top, that would be V initial in this case here. Because we have a question, we do that too. But for now, just remember this is V final. Now, I need you to take some notes at this point here. So this is the equation that we use. It is equal to 2gh1 plus c. Now you already know what is c, right? But remember, this is only for those that is only for those objects that are rolling down. What if the object is not rolling down? Okay? What, or let's just write this one here. We'll say if the object is not rolling, it has no moment of inertia. Or you can say moment of inertia would be 0. In other case, we can say C for that case is going to be 0 here. So now what will it become, the equation, if the object is not rolling? So we can say if the object is not, once again, if the object is not rolling, then this equation becomes V, it is equal to 2gh over 1 plus 0. But what is 1 plus 0? Isn't that still 1? Yes, if it is 1, 2gh over 1, that is still 2gh, so we'll just write 2gh. That'll be the equation here. That is for an object. You can say that is not rolling. So let's add a few more keywords to this one here. If it is not rolling, you can add. If it is falling, if it is slipping, you can say if it is sliding to. Okay? And if the question says on a smooth surface, but remember, if they ever mention a smooth surface, they must mention that there is no rolling if they ever did. If not, just look for these keywords. If it is not rolling, if it is falling, if it is, let's say, skipping, if it is slipping, not skipping, if it is slipping, if it is sliding, let's add one more word here. If it is dropped as well. If dropped from rest, let's say. These keywords, it means there's no rolling. And if it is not rolling, then the equation above becomes 2gh. In other words, we can say, if an object is, if the objects are not rolling, all objects would have the same velocity once they reach the bottom of the equation. If the objects are not rolling, then they all have the same what? The same translational speed. Translational speed once they reach the bottom, let's say. Or at the bottom. Same translational speed when they reach the bottom. Of the incline, let's say. Even if they're dropped. Right? So I hope you took this note, and I need you to be very careful with this one here. So now I can give you an example here. If an object, okay, we're dropping two objects. One of them is a solid sphere. Why don't we just bring this one here? This is a 3D, so this is we can say solid sphere here. And this is I don't know, you could say a disk. What is the difference between the two? Moment of inertia for solid sphere, that is going to be 2.5. Wow, 2 over 5 mass times radius squared, but the moment of inertia for this one is going to be 1 over 2 mass times the radius squared. Assume that these two have the same radius and the same mass, Basha. So, once they fall, for example, which one of them would hit the ground at a faster speed, let's say? The answer is both of them would have the same speed. Do you know why? Because we just said that velocity, if they're not rolling, it is equal to 2gh. So it does not depend on the shape, it does not depend on the mass or the radius. The only thing it depends on is the height. And if we assume that these are falling at the same height, then of course they will always have the same translational speed regardless to their shape, regardless to their mass as well. Even if they don't have the same mass and radius, they will always end up having the same translational speed. Now this, of course, would lead to the next question at this point here, and that is this. What about if these objects are rolling down here? Let's say the height is 3 meters. Okay? What would be their translational speed if they are rolling down here? So here's what happens here. So what is going to be the translational speed of each one of these if they're rolling down? Let's talk about the first one, if it is the solid sphere here. Solid sphere. If it is a solid sphere, so the translational at the bottom, it is equal to the radical of 2gh 1 plus c, right? So once again, square root of 2 times g is 9.81. You do know that. What is the height? Let's just say it is 3. And then 1 plus, what is c for solid sphere? Remember, we said c for the shape, right? That is 2 over 5. Now you could do the number here. All right, what about for the second shape in here? Let's just say it is a disk. If it is a disk, we can say translational speed at the bottom, it is equal to the radical of square root of 2gh 1 plus c. See, you don't have to do or to go through all the equations of mechanical energy, initial equal to final, and then do all the steps. Eventually, you'll get into this step here. So we just kind of like skip few steps, and then we'll just jump right to the last step, which we have this equation. It is equal to 2gh, that is 2 times 9.81 times 3 divided by 1 plus 1 over 2. That would be for a disk. Now, of course, you could do the math and see which one of them is greater once they reach the bottom here. And clearly, we can see that the less this number, that would be the bigger the translational. So, of course, this one must be larger than this one here. Oops, the other way around, by the way. So the tangential speed for this one is going to be larger than this one right here. All right, but there's one more thing which I would like to mention here, and that is this. As a matter of fact, let's just keep this one here on the screen. Let's go to another page. When objects are, if the object is rolling down at incline, whatever the shape is, so what does it depend on, or what does the translational speed of the object at the bottom of the incline depends on? That is also something very important you need to know. Didn't we say the equation is 2gh 1 plus c here? So what it depends on, we can say it depends on the height. That's one. It depends on the shape of the object. And we can also say that it depends on the gravitational acceleration. It's a constant, by the way, but what if we just do this on a different planet? Like could be on Mars or Jupiter, whatever, or could be even on a moon, let's say. So if we just do that in a different place where gravity is different, then we can say it depends on that too. Otherwise, this is a constant and we don't mention that much. Okay, so what are the things that it does not depend on? It does not depend on the mass of the object. It does not depend on the radius of the object. So whatever the mass or the radius, so the translational speed does not depend on it. The only thing that it depends on is it depends on the height, it depends on the shape of the object, and also depends on gravitational acceleration, we can say, if the space or the location is changed in here. Okay, but sometimes what if the question asks for, that is for translational, right? What if the question is asking for the angular speed of the object? Then, well, that would be easy, right? Because angular speed, it is equal to what? Tangential times, my bad. Okay, what if the question is asking for angular? We know that tangential, it is equal to angular times the radius, yes? What if you want, or the question asks for the angular speed of the object? Well, in that case, angular speed of the object, it is equal to tangential divided by the radius. Then, if the question is ever asking for what does the angular speed of the object at the bottom of the incline depends on, then of course you can add all what we have just said. We can say the height, right? The shape of the object. We can also say, now we can say the translational speed as well. And then you can add the radius too now. Okay, so these are what it depends on. You can add gravitational to if the place is changed as well. So these are what it depends on. These are some life-saving notes, and I hope you took your notes carefully. Now I think it is time to solve some questions, right? Because I've talked a lot, and we need to get into some practical work in here. So this is mechanical energy, is the sum of all the types of kinetic and potential energy, of course. So this is what it is. Mechanical energy may be conserved if we assume there's no friction, no air resistance, nothing to slow the object down. If that is the case, we can say mechanical energy here. Well, what exactly mechanical energy here? We only have potential if the object is at rest, kinetic energy of translation is 0, rotation is 0, but once it gets to the bottom, now potential is 0 because the height is 0. Now we would be having kinetic energy of rotation and translation. Okay, so and this is what I just did for you earlier here. I said for rotational kinetic energy, we can write C times kinetic energy here as well, which I believe you'll remember. And then we took kinetic energy as a common factor. instead of all this, we'll just write V final that is equal to the square root of 2GH divided by 1 plus C. This C represents the shape. Sometimes you can even simplify this. We know that G is constant as long as it is on Earth. We can write 19.6 times the height, but I don't recommend this. I just recommend the main equation. That'll be way better. Few study tips, which I already talked about. When it says on smooth slopes or when the object experiences slipping, they have zero kinetic energy of rotation. That is the case, C0. So solar spheres, hollow cylinders, rings, and disks all reach to the bottom of the incline simultaneously. That means at the same time, and have identical speeds. Right? We've mentioned that. So why? Because mechanical energy at the top equal to mechanical energy at the bottom. There we only have potential at the bottom. Now we only have translational kinetic because the rotation is zero. So we'll end up with this equation here. So once again, remember, if the question says there's no rotation or gives you any indication that there is no rotation, the equation becomes, or V translational at the bottom becomes 2GH only. So these are for all the shapes, you can see that. So all the shapes will have the same translational at the bottom. The speed of the solar sphere, hollow sphere, ring, and disk depend only on the height of the object in that case, and gravitational acceleration if the place changes. But watch this, if the surface is rough, a moving object will experience or will have both translational and rotational kinetic energy. A ring, for an example, what would be the translational kinetic energy of a ring, for example, at the bottom of the incline? Here's the equation, right? If it is a ring, let's just say if it is a ring, what would be the equation for a ring? V final, we can say, it is equal to the square root of 2GH 1 plus C. What is C for a ring here? Isn't that just 1? Yes. So V final, it is equal to, we can even simplify this equation if you want to. 1 plus 1, that is 3 minus 1, right? So you could just cancel out the 2 here. So what would be the equation that you're left with? GH. You see, a lot of students memorize a lot of equations here, the ones that I wrote, but you really don't have to memorize anything. Just memorize one equation and that's it. Once again, a lot of students are memorizing this table, which I don't really recommend as long as you have this equation and you know the moment of inertia for the shape, and that's it. So it works for any shape and that's it. You don't have to do anything else. And of course, there are different methods you could do that. But just memorize this and that saves you the whole thing here. And that's it. All right. So you could try for any shapes, by the way. Let's just try a few shapes. We said for a ring, it is equal to V. It's equal to what? 2GH, right? All right, so you don't have to memorize, by the way. Where do we get this from? So radical of 2GH 1 plus C for a ring. Let's just extend it. 2GH 1 plus C for a ring is just 1. Then you could just do the math. What about for a ring? What about for a disk? Once again, that's 2GH 1 plus, for a disk, that would be 1 over 2, right? And that's it. What about for a thin spherical shell? Thin spherical shell, like a basketball. Oh. Thin spherical shell. That would be the square root of 2GH 1 plus, what is C for thin spherical shell? Isn't that 2 over 3? Khalas. What about if it is a solid sphere? That would be 2 over 5. Oh, whatever. By the way, let me just say one more thing. If you use this equation by any means and it turns out it doesn't work, then please use the classic method. You can say, what is the classic method or whatever? You just use the longer method here, which in this case, mechanical energy initial. You can say it is mechanical energy final. At the top, you would have what? You have potential energy only at the bottom. If it is, by the way, actually, remember something very important here. Okay, we were using this, that is, if the object is always at rest, then this is the final translational speed that we were finding here. So if the object is starting at rest, we would only have potential energy. And then at the bottom, we would have kinetic energy of translation plus kinetic energy of rotation. And then you could do the rest of the method in here. But what if the object is already moving, if it is not at rest? And that changes the whole thing, as a matter of fact, in here. If the object is already moving, which we don't have any questions like this, by the way, but, you know, it's wizari, you know, like, it is unpredictable. So what if, yani? In that case, of course, mechanical energy initial is going to be what? It's going to be the whole thing. If the object is not at rest, mechanical energy initial, it is equal to final. In that case, of course, we'll have to say kinetic energy of translation plus kinetic energy of rotation plus potential energy. These are all initial. It is equal to kinetic energy of translation plus kinetic energy of rotation plus potential. Actually, the bottom here is going to be 0. They could ask for any other points, even if it is not 0. Well, that is the equation that you need to, you know, like use at this point here. I would say whatever is known or whatever is given, you could just plug it into the equation and that's it. By the way, don't worry much about this, but just have this in mind, Danny. Just, let's say if God forbid, they brought anything similar to this, now you have an idea at least what to do, so that it's nothing, you know, like surprising at this point. But like I said, try not to worry much about this because we don't have any question or any case. It's never been in Uzari, this method here. But now I believe you know an extra way just in case what to do if they ever brought this now. Otherwise, all the other things that we have is we'll just use the main equation and khalas. And these are the rest of the study tips that I was talking about. Now I think it's time to solve a few questions here. Watch this. The first question that we have, it says we have a solid ball. Now it's very important to know what shape is this because we'll need it for the equation here. Okay. It says a solid ball with a mass of this much. Like we said, there is no mass in the equation. We don't need that. But because it says a solid ball, what is the moment of inertia for a solid ball here? Moment of inertia for a solid ball, it is 2/5, like a bowling ball, correct? Mass times radius squared. We just need this factor here. Okay, but keep that in mind. It says with a mass of this much, we don't need the mass of this one. Radius, we don't need it. Starts from rest. That is very important. That is a keyword. If it starts from rest, that means we can use the equation safely without any problem now. Starting from rest, that means V initial is 0. That's a relief at this point. At a height of, it is very important to check if the height is not given. If it is given, that's a good thing. If it is not given, that would be, it will require an extra step. But again, that's nothing for you to worry about at this point here. That is, this rolls down let's say down an angle or a 30-degree angle slope. What is the translational speed of the ball? What is what? What is the translational speed? What does it mean? When it leaves the incline, that'll be V translational when it leaves the incline. So here V final you could say. Let's see if we could write. Okay, so that is going to be V final. Why V final? Because initial was 0. Okay, so what is V final? That's it. Now we said there is only one equation you need to know or remember. And what is that equation? Good man. V final. That is equal to that's too much. Square root of 2GH1 plus C. And that's the only thing you need to know. 2 times 9.81. What is the height? 2 meter? Well done. 1 plus, what is C for a solid ball? We said it is 2/5, right? Now this point here, try not to be smart and don't do all these numbers at once. No, do that at steps, okay? Now, once you do this, of course, you can find V final. What is V final equal to? Whatever it is equal to now, you could just do the number. So what is C? Let's see, what is it equal to? It is equal to 5.29 meter per second. 5.29 meter per second here. And that's it. Okay, so this is V final. But what if, let's just add this one here. What if the question is saying, okay, what if the question is saying the object is slipping? If by any chance says the object is slipping, then this equation would have became 2GH 1 over c, because there's no rotation, right? You could have just wrote actually 2gh. You don't even need that. So if that would be, if that was the case, 2 times 9.81 times the height, which is 2. So let's see what is this equal to. 4 times, let's get a calculator first. That is 2 times 9.81 times 2. Or you could just say 4 times 9.81 under the square root. 4 times 9.81. The answer would have became 6.26. Or you could say 6.3. Okay, 6.3 meter per second. See the difference? Actually, this reveals another secret regarding, or another key regarding this tree here, which that'll be my next point here. Okay, so V final, if it is rolling, that'll be 5.29, 5.3 about. If it is not rolling, slipping, that is going to be 6.3. Do you see the difference between the two now? Yeah, so this is clearly the answer now. But I want to tell you something different now, and that is this. If we have two objects, or let's say an object actually, or it could be two identical objects, doesn't matter. One of them is rolling, and the other one is falling. So here, okay, as a matter of fact, all right, let's just bring this one here. We have two objects. These are identical. That means they have the same mass, the same radius, the same shape and everything. But one of them, it is rolling, okay? And the other one, it is just falling here. So once they reach the bottom of the incline here, which one of them, I think I talked about this one here, right? Why do I feel like I've talked about this one here? Once they reach the bottom of the incline, V final and V final, which one of them would have a larger speed? I feel like I've talked about this one. The answer is this one. Why is this one? I mean, I should have asked you first, actually. Do you think one of them would have a larger speed than the other one, or they would both have the same speed, or one of their speed would be larger than the other one? By the way, these are both the same height. Okay, you can say a height of 3 meters, doesn't matter. But one of them, it is rolling. The other one is just falling here. We said if it is falling without rolling, perhaps I didn't talk about this, the equation becomes 2gh, right? What about if it is rolling? The equation becomes the square root of 2gh, 1 plus c. Let's say this is a disk. Well, it could be anything. All right, the disk or solid sphere, doesn't matter. Okay, let's say a disk. That is going to be 1 over 2. Can we find their speed? So that is going to be, I think this is x. Yeah, let's say 2 times 9.81. Let's say the height is 3 meters. 1 plus 0.5. Yeah. What about this one here? It's going to be 2 times 9.81 times 3 here. So this one would have a larger speed, but you can tell obviously now. But here's my next question: why that one would have a larger translational speed? Okay, so square root of 2 times 9.81 times 3. For this one here is going to be 2 point about, the translational speed for this one is going to be about 2.8 meter per second. What about this one here? Let's do this one too. That's the square root of 2 times 9.81 times 3, because it's the same height, divided by 1 plus 0.5. The answer for this one, it is equal to 5.4. What a surprise. Meter per second. Isn't that the same shape, the same object, it's the same height too? But why the speed of this one? Weren't they supposed to have the same speed? You can see that. Why the speed of this one, if it is rolling, it is less than the speed of this if it is falling. Like, what makes for the difference here? Why are they different? Think about it. What causes this difference? Well, the answer to this, after you gave it a, I don't know, perhaps a deep thought here, but because this one, while it is rolling down here, we can say part of this energy converts to the rolling here. In other case now, because of the rolling, part of its energy would be lost due to rolling, so it will end up with less energy here That is why the velocity for this one, if it is rolling, would be less than that if it is not rolling. We said if something is dropped, it is not rolling. So all that potential energy will convert to kinetic just right before it hit the ground. So it would have a larger translational speed at the bottom. But for this one here, I write 2.8. Oh, let's just fix this one here. That's 2 times 9.81. Wait a second. 2 times... Oh, did I just say 2 times 2? No, that is 2 times 3, because the height is 3. 2 times 3 times 9.81. Oh, thank God I saw this one. That is 7.67. 7.67. See the difference between the two here? 7.6, you can say 7.7 by rounding if you want to do that. And this one is 5.4. So why the velocity of this one is larger than this? Again, we'll say because as this object is rolling down, part of its energy tends to converge to the rolling. This is why the object will end up having less translational speed for this one. But because there's no energy converted to rolling, so this one will have a larger velocity as it hit the ground here. All right, so remember this. And yeah, that's what it is. Okay, that was a good question actually. All right, so now here are the answers in both methods. You could use this one here, or you could just use this one, and it works with all the examples, inshallah. And this, it tells you if the object does not roll, what would it be the velocity? That would be this much, and you can see that this is larger than this one if it is not rolling down. We have this Wazari question says, if a solid ball rolls down from the top of an inclined plane of height of 2 meters at the bottom, let's say to the bottom of it without slipping. And in the second case, it says without slipping. Okay, so a solid ball rolls down from the top of an incline down a height. So here's what it is. It is going to roll down. The height is 2 meters. Okay, and then it says without slipping. In a second case, another time, it falls down freely from this. Now, the second case, it is going to fall down from the same height. So the question says, by neglecting air resistance, the final speed of the ball center says what? Now, there are two cases, right? It depends on its mass when it's rolling down. No, because we said final speed, it is equal to 2gh over 1 plus c if it is rolling down. But if it is not rolling down, it is just 2gh, right? Yeah, so let's see what it is. That is for rolling, and this is, we can say, without rolling. Without. Okay, the second one says they are equal. Are these two equal if it is falling or rolling down? The answer is no. C says, will be greater when it rolls down. Is it true? The answer is no. We said if it is rolling down, it's going to be less. Part D says it will be greater when it falls freely, and that is the correct answer here. Okay, I believe that'll be the end for this session. Inshallah, in the next session, we're going to start with this example. Or maybe I can solve this one too, actually. Let's just solve this one too, because next time I want to start with something easy. Okay, even though perhaps. Yalla day. Says a 1.5 kilogram bicycle tire, be careful. Says a bicycle tire looks like a ring. Sometimes they'll give you the equation too. So you just have the factor, the equation. You could just, that makes it even easier to use this. So it starts from rest. That's a good thing, right? So now we can use the equation. Rolls down from the top of an incline that is 14.8 meter high. What is the translational speed? What is V final of the tire when it reaches the bottom of the hill here? So we said, just use the equation. V final, it is equal to the square root of 2gh plus 1 over c here. Once again, 2 times 9.81 times the height, which is 14.8, divided by 1 plus c. What is c for a bicycle? It is just 1. It says consider or assume that the tire is a hoop, or a thin hoop with the moment of inertia 1 times mass times radius squared. So all you have to do, that would be 2 and then it cancels out with this tree here, so just 9.81 times 14, and then do the math. Of course, you'll find the answer is going to be 12 meters per second, and that is V final once it reaches the bottom of the incline. That'll be the end of this session. Keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.